And welcome back to the last podcast in this section 13.1. We're dealing with the nature of gases. So far in this unit, we've talked about the kinetic molecular theory, some of the assumptions that we make about gas particles that are eventually going to help us to describe how these things behave. We've also talked about, in the last podcast anyway, we talked about gas pressure and how we measure gas pressure, at least atmospheric pressure. And in this last section of 13.1, or at least the last podcast of this section, we want to talk about how the kinetic energy of the particles is related to the temperature. And when we're dealing with temperature, we're actually dealing with it on the Kelvin scale, because that is the absolute temperature scale. Now, this first diagram that we want to look at is pretty interesting because it shows us the distribution of speeds of particles at different temperatures. Let's take a look at the blue line first. With this blue line, we're looking at lower temperatures, and you'll notice that at any given temperature, the particles are not necessarily moving at the same speed. The height of this talks about the relative abundance, or the percentage of molecules moving at a particular speed, and on the x-axis here you have the different speeds. They talk about it in terms of kinetic energy, but remember, kinetic energy is related to the velocity, the square of the velocity anyway. So what this means is the majority of the particles are moving at a speed with that amount of kinetic energy. There are some particles up here that are moving with more kinetic energy, and there are some particles down here that are moving with relatively little kinetic energy. And then there's a whole distribution. But the majority of particles have a moderate amount of kinetic energy. Some are going very fast, some are going very slow. Now, as you warm up say in this case, a thing of water, the average speed of the particles is going to increase. Notice that the average, if we draw a line right down the middle here, has in fact got faster. It's shifted to the right. They have more kinetic energy at higher temperatures. But the other interesting thing is that the speeds start to distribute themselves more. There's actually a lower percentage moving at moderate speeds. You have more and more particles that are going faster, and you have more and more particles that are going slower. The distribution spreads out. If we were to have even warmer temperatures, let me see if I can't change the color on this. Oops, minimize the wrong thing. Hang on here. There we go, we're back. And if I change the color here, let's go red hot. If you heat this thing up even more, the distribution is going to look like that, where it flattens out even more. The speeds are spread out incredibly. If we cool this thing way down, and let's go to, say a royal blue or whatever, the distribution, if it gets really cold, is going to look like this, where they're all bunched up. The slower, the colder the temperatures, the more similar the speeds are. Now let's talk about why this is, or at least an analogy that can help us understand this. If we have a moderate temperature, the moderate temperature is, say, analogous to driving on telegraph. Okay, we'll just call this Telegraph Road. Telegraph Road has a speed limit of 35 miles per hour. Now, does everybody drive 35 miles per hour? No. There will be some people that are driving 45. There will be some people that are driving 40. Most people are driving right around 40. And there will be some people that are driving 35. Very few people will be going less than the speed limit. All right? Now, if you go to a colder temperature, we'll say that this is a residential. Okay, in that residential, let me kind of draw this over here, the speed limit is 25 miles per hour. Some people might be driving, say, 27 to 30 miles an hour. Very few people will be going faster than that. Occasionally, even, some people will be driving less than that. But not too many. Pretty much everybody's going to be driving at least 25 miles an hour. Notice that there's only a little 3 to 5 mile an hour window that people are driving in. If you look at cars going down a side street, a residential, they're all going pretty much the same, with just a little bit of a variety. As you increase the speed limit, there becomes more variety in speeds. You may have a 10-mile-an-hour difference on telegraph. Yes, there will be some cars that are going really, really fast, but not too many. Yes, there will be some cars that are going really slow, but not too many. Pretty much everybody's driving between 35 and 45. Now, if you go to a really hot temperature, this is, say, I-75. I-75 has a speed limit of 70 miles per hour. But on I-75, you're going to have people that are driving near 80 miles per hour. Don't recommend it, but they will. And there will be people that are driving even down near 60 miles per hour. So there's a big gap of speeds on the highway. So the analogy is this. The lower the speed limits, the lower the temperature, the closer together all the speeds are. The higher the temperature, the higher the speed limit, the more distributed the speeds are. Now, to finish this off, let's kind of put this in paragraph form. Let me scroll down a little bit more. Here's our little paragraph here. The Kelvin temperature or some people say the absolute temperature of a substance is directly related or proportional to the kinetic energy. Or you can think about it in terms of speed, but we know that it's related actually to the square of the speed, but that's not the point right now. This means that if the temperature is doubled, then the particles are going to have twice the amount of kinetic energy, which means that they're going to be going faster. Actually 4 times faster, but we're not going to ask you to calculate all that. The main idea is simple. As you increase the temperature, the average speed of the particles are going faster. As you lower the absolute temperature, the average kinetic energy of the particles and the average speed of the particles will be slower. That concludes 13.1.